This is a modern microchip, and inside it is a problem that almost stopped technological progress. Zoom in, and you see thousands of nanoscopic layers stacked on top of each other. At the very bottom of that maze sit the transistors, switching billions of times every second. For 50 years, the rule was simple. Shrink the transistor, and everything gets faster. It worked beautifully until it didn't. As a chip design engineer, I can tell you we are now running out of space at the atomic level. We print chips with light, and the light we use is already far too big for what we are trying to draw. Everything blurs, and a blurred pattern is a dead chip. But right at this wall, a strange idea appeared. What if we stopped drawing the pattern and let the material draw itself? It sounds like science fiction. It's already inside a real factory, and only one company on Earth is willing to bet its future on it. Subscribe to the channel and let me show you. Start with why scaling broke, because most people get this part wrong. To build a chip, you have to print patterns onto silicon using light. At normal scales, light behaves exactly as you expect, a clean beam. At the nanometer scale, it behaves like a wave, and a wave has a fixed width. Visible light is 400 to 700 nanometers. Modern chips print features far below 10. Just think about that. The brush is 100 times bigger than the line you're trying to paint. And at the same time, the transistors themselves started to fail. They work by controlling electrons with a barrier. Make that barrier a few atoms thin, and the electrons stop respecting it. They tunnel straight through. The switch never fully turns off. It leaks. And in microchips, leakage sinks ships. The industry was cornered, so it went to extremes. It moved to extreme ultraviolet lithography, light with a wavelength of just 13.5 nanometers, around 30 times shorter than visible light. Suddenly the brush is sharp again. And to understand why this machine changed everything, you have to see what it takes just to make that light exist. You cannot buy 13.5 nanometer light. You have to create it. So inside the machine, molten tin droplets are fired through a vacuum, tens of thousands of them every second, each one smaller than the width of a human hair. Each droplet gets hit twice by a laser. The first pulse flattens it into a pancake. The second one vaporizes it into plasma at roughly 220,000 degrees, about 40 times hotter than the surface of the sun. And that plasma emits the light. This isn't a lamp. It's a controlled explosion, repeating tens of thousands of times per second all day, every day. Then it gets harder because these photons are almost impossible to handle. They get absorbed by air, so the entire optical path has to be a perfect vacuum. They don't pass through glass, so lenses are useless. Instead, the light bounces off a series of mirrors so precise that if you scaled one up to the size of Germany, the biggest bump on it would be under a millimeter. And even those mirrors absorb roughly a third of the light on every bounce. After a dozen reflections, only a few percent of what you generated is still alive by the time it reaches the wafer. But that tiny surviving fraction carries the pattern. It hits a wafer coated in photoresist and rewrites that material at the molecular level. You wash it, and what survives is the design. One layer done, then you repeat it hundreds of times, and every single layer has to line up with the one beneath it to within a fraction of a nanometer. There is no room for error. You are building structures atom by atom, and you're doing it with starlight you manufactured yourself. That machine carried the industry through the last decade, but now it's fighting physics again, and this time it's starting to lose. Here's why, and this is the part almost nobody talks about. At this scale, light doesn't arrive as a smooth wave. It arrives as individual photons, and you can count them. Every tiny feature you print is defined by a limited number of photon hits, which means randomness gets a vote. Some spots catch a few more photons, some a few less. At 40 nanometers, that difference is invisible. At 8 nanometers, that difference is the whole feature. A line pinches and breaks, a contact hole closes up and never opens. Statistics start killing your chips one at a time in random places you cannot predict. The industry calls these stochastic defects, and they are the single ugliest problem in modern patterning. There's an obvious fix. Throw more photons at it, turn up the dose, and the randomness averages out. And it works. It's also brutally expensive because dose and speed are the same dial. Crank the dose and the scanner exposes fewer wafers per hour. ASML's newest high-NA machine runs around 175 wafers per hour at a dose of 50 millijoules per square centimeter. Double the dose to clean up your defects, and you've just cut that number roughly in half. Now think about what that costs. A standard EUV scanner runs well over $200 million. The high-NA version costs about $380 million. That tool has to be running, printing, earning every hour of every day. Every wafer you don't expose is money burned. So the honest picture is this: we can print the pattern. We just might not be able to afford it. And this is where Intel walks straight into the trap. Their 18A node is already in high volume production at Fab 52 in Arizona, running Panther Lake, and it does that on standard EUV. Fine. The next one is where it breaks. 14A is designed to be the first process node in history to use high-NA EUV in real manufacturing. The 0.55 numerical aperture optics get you down to 8 nanometer resolution instead of 13. That sounds like a clean win. It isn't, because Intel's own finance chief has already confirmed the obvious. 14A will be more expensive than 18A, and the high-NA tool is why. You bought the sharpest brush ever built, and the physics still forces you to paint slowly. So you need something else. Something that doesn't come from lithography at all. And the answer Intel picked is genuinely one of the strangest ideas in chip making. If light can't do it, the material has to. This is directed self-assembly, or DSA. And the secret behind it is a class of materials called block copolymers. Picture a molecule built from two halves that chemically hate each other, chained together so they can never separate. Polystyrene on one end, PMMA on the other. They want to get away from each other, and they physically can't. So the system sits in tension. Now you spin that material onto a wafer and heat it. The molecules start moving, and they resolve that tension the only way they can, by sorting themselves into repeating patterns. Lines, dots, cylinders. Perfectly uniform at exactly the scale chip making needs, because the size of the pattern is set by the size of the molecule, not by a wavelength, not by an optic, by chemistry. Think of it as a Lego set that builds itself the moment it gets warm, and it's fast. At IMEC, that assembly step finishes in about 60 seconds on production-grade track equipment, not on a lab bench. And this is where the numbers get interesting, because that molecular size is a dial you can turn. The workhorse material, polystyrene with PMMA, naturally settles into lines around 20 nanometers wide, and it can be pushed down to critical dimensions near 9. To go smaller, you need the two halves of the molecule to hate each other even more. Chemists measure that hatred with a value called chi, and raising it lets the pattern shrink further before the material gives up and stops separating cleanly. That's why the second generation of these high-chi polymers, developed with suppliers like Merck, Brewer Science, and Nissan Chemical, was the unlock. Higher chi, tighter pitch, sharper walls. But there's a catch, and for years it was fatal. Left alone, those patterns are beautiful and completely useless, because they organize locally in random orientations like fingerprints. In chip making, position is everything. A perfect line in the wrong place is a defect. So you don't let it choose, you guide it. First, you use lithography to print a coarse guiding template, a set of rails at a pitch the machine finds easy. Then you apply the block copolymer and heat it. Now the material self-organizes, but it's constrained. The template grabs every few lines and locks the phase, and the chemistry fills in everything between them. And here's the beautiful part. The material multiplies your pattern. You print a wide, sloppy, cheap guide, and you get out a dense, sharp, narrow one. IMEC demonstrated exactly that, using a 90 nanometer guide pattern to produce 18 nanometer pitch lines. Read that again. The final pattern is 5 times finer than the thing that directed it, and the guide was printed with old immersion lithography, not even EUV. That is what breaks the deadlock. You are creating features far smaller than the light that made them. And there's a second gift hiding in this, one that engineers care about more than the pitch number. Lines printed with light are never straight. Look at them under a microscope and the edges wobble, and that wobble is a direct source of variation and failure. When the block copolymer takes over, the edge is defined by where two chemistries meet, and that boundary is far smoother than anything a photon can draw. In IMX work, line roughness improved by a factor of roughly 2 to 3. So you're not just getting smaller, you're getting cleaner. Of course, none of that matters if you can't transfer the pattern into the actual chip. And this was the hard part. You've now got polymer lines that are extremely tall and extremely narrow, and the moment you start etching, they want to fall over like dominoes. Solving it took custom etch chemistry developed together with Tokyo Electron to drive that pattern down into a 60 nanometer thick silicon nitride layer without a single line collapsing. That's the unglamorous engineering nobody puts on a slide. And it's exactly the kind of thing that decides whether a technology is real. Now put that together with the money problem, and Intel's logic becomes very clear. If chemistry sets the final line width and cleans up the roughness, then the lithography step no longer has to be perfect. It just has to be roughly right, which means you can drop the dose. Intel's own research has demonstrated dose reductions of 50% and more, in some cases pushing down toward 25 millijoules per square centimeter, a 3 to 4 times cut. Cut the dose, and the scanner speeds back up. More wafers per hour out of a $380 million machine. Better line edges, fewer random defects. That is the entire bet. DSA is what makes high-end A affordable. But how far is this from real production? You'd assume it's a research curiosity years from a fab. You'd be wrong. DSA first showed up on the industry's official roadmap back in 2007, and then it spent more than a decade going nowhere. The reason was always the same one word: defectivity. A missing line here, a dislocation there, and at billions of features per chip, almost perfect is not a thing. So the industry moved on, except it never fully died. IBM, IMEC, Intel, Tokyo Electron, and CEA Leti all kept 300mm DSA pilot lines running on real production wafers. And Sony did something nobody else did. They built a back-illuminated CMOS image sensor with a DSA process. The first production-grade image sensor made this way. That matters more than any paper because it proves the chemistry survives contact with an actual factory. The materials work. The anneal works. The pattern transfers into the layers underneath without collapsing. And the economics behind it are not marginal. Because this is a chemical process, wafers can be run in batches rather than one at a time through a $380 million scanner. And studies of DSA in silicon front-end processing have put the savings around 17%. In an industry where a single point of margin is fought over for years, 17% is not an optimization. It's a different business model. That's the easy case though, and I want to be honest about it. An image sensor is a repeating array. It's regular, forgiving, and DSA loves regular. Leading edge logic is the opposite. It's irregular, it's dense, and every single one of those billions of features has to be exactly where the design says it is. Pushing self-assembly into logic is a completely different sport, and there is exactly one company willing to play it. Intel is targeting 14A for risk production in 2027, with high volume manufacturing in 2028. And they've already installed the industry's first commercial high-end A machine, ASML's TwinScan EXE5200B, at their Oregon development site. Early versions of the design kit are already out with lead customers. Several of them have plans to tape out 14A test chips, and multiple companies have said publicly they intend to build on the node. So this isn't a slide. The tools are bolted down, the wafers are running, and the company has publicly called 14A the node that decides whether Intel Foundry becomes a real business or not. They are betting the company on letting materials assemble the most advanced chips on Earth. And the rest of the industry is not following them. TSMC has said repeatedly and publicly that it does not need high NA for its 1.4 nanometer class node, a 14 which arrives around 2028. They'll get there with the low NA tools they already know using multiple patterning, and they'll eat the extra process steps because those steps are predictable. Samsung has pushed its own 1.4 nanometer plans and its high NA volume adoption out toward the end of the decade. Nobody at the leading edge is planning to put self-assembling polymers into their critical logic layers. They're betting that brute force wins. And you have to understand why that's a completely rational position. At millions of wafers per month, predictability beats elegance every single time. Multiple patterning is expensive, and everybody knows exactly how expensive. DSA is cheaper on paper, and nobody knows exactly how it fails at scale. And the failure mode is nasty, because at 14 angstroms, chemistry that is 99.99% perfect is still catastrophically imperfect. A trace of contamination, a slightly wrong surface energy, a thermal gradient across the wafer, and your material assembles into the wrong thing everywhere at once. Lithography errors are usually local. Chemistry errors are global. Here's the part most people miss though, and it's why this fight is bigger than one node. EUV and DSA are not just two tools, they're two opposite philosophies of how you build matter. With lithography, you control the outcome from the outside. Every photon, every mirror, every nanometer of stage motion is commanded. It is pure top-down engineering, and it has been the religion of this industry for 50 years. DSA is the opposite. You don't command the final structure at all. You set up the conditions, and then you let the system find its own lowest energy state. The pattern isn't drawn, it emerges. You stop being the artist and start being the person who builds the frame. So ASML's machines stay exactly where they are at the center of everything. They still define the frame, but DSA acts as an amplifier, extending what that frame can hold long after the light has done all it can. And that's how you slip past a wavelength you cannot shrink any further into the angstrom era without waiting for a machine that doesn't exist yet, which leaves us with a genuinely open question. Two of the three companies left on the leading edge are betting that you can force light to keep doing the job, whatever it costs. The third is betting that the job has to move to the material. One of those bets is wrong, and we find out around 2028 on real wafers with real money. If Intel is right, 14A gives them a cost structure their competitors can't match, and the comeback is real. If the chemistry doesn't hold at scale, they will have spent billions learning that the industry was right to walk away from DSA the first time. So which side would you take? Does the future of chip making get drawn, or does it get grown? Tell me what you think in the comments. I read them. And if this was worth your time, the best way to support it is to share it with someone who still thinks Moore's Law is dead and subscribe to the channel.